Points can move. Slide, flip, turn, stretch. Coordinates keep score.
Watch the scene first. The math is built into the environment, where every reed and stone records precise measurement of movement through space. This top-down view shows the lagoon as a coordinate grid. To track a geometric translation, we begin by identifying the starting point. Here, the stone block at 2, -1. When the turtle slides left across the lily pads, it moves 5 units in a negative direction. This physical action corresponds to subtracting 5 from the starting x-coordinate. The path then turns upward. Moving 3 units along these mossy steps means adding 3 to the starting y-coordinate. 2 minus 5 gives us an x-coordinate of -3. -1 plus 3 gives us a y-coordinate of +2. The physical movement results in the coordinate -3, 2. Translations are direct arithmetic adjustments. Moving an object's position in the lagoon requires this additive or subtractive logic, changing where the object is without altering its shape. Reflections operate differently. Instead of sliding along a path, the transformation mirrors across a fixed boundary. The waterline acts as the x-axis. A point sits above water at -4, 3. Reflecting across the waterline alters vertical depth, dropping straight down while maintaining grid alignment. The x-coordinate remains -4, but the y-coordinate shifts underwater, reversing to -3. This inversion shows how reflection preserves the object's distance from the waterline while reversing spatial orientation.
A flip changes signs. A slide adds. Watch each coordinate.
Rotation requires a different mechanic. It involves moving the entire space around a central origin point. From above, we see a circular lily pad centered on the origin. A target point sits on a pedal at 3, 2. For a 90-degree counterclockwise rotation, the x and y values swap positions, and the new x-coordinate becomes negative. Apply that rule to our starting values of 3 and 2. Swapping them and changing the sign of the first value creates what new coordinates? The values swap, and the 2 becomes negative. The physical quarter turn lands at -2, 3. The swap between coordinates tracks the quarter turn exactly. This notation provides a consistent way to determine the new location following the rotation. Each transformation, sliding, flipping, or turning, is tied to a specific algebraic change. The linear paths, reflective drops, and circular arcs we see are all recorded by these coordinate rules. Look at the environment one more time. Which specific marks in this scene prove the mathematical relationship, and how does the physical action make that geometry true? Mathematical notation records physical movement. It provides a universal language to track and verify every spatial change in the environment.
The rules are simple. Coordinates never lie. Transform a point yourself.